Hi everyone, I'm Tim Wang from Tsinghua University, and I will introduce the IMACLIM-China and China-Mo models. First, I will introduce the background of the modeling work. The IMACLIM-China belongs to a top-down model, or simply called TD model. As a general equilibrium model, IMACLIM-China can represent the input-output relationship among different economic sectors. Suitable for macroeconomic analysis of climate policy, including carbon tax and carbon markets and so on. As we know, the CGE model describes the substitution relationship between inputs based on electricity. But this substitution relationship is not achievable in actual world, especially considering the limitation of technologies. That's how the industrial process CO2 emissions and non-CO2 GHG emissions are usually characterized based on the values of sectors in the CGE model. So it can cause a low accuracy when concerning the projection of these gases. The China-Mo model is a bottom-up model, or simply called BO model. Compared to the IMACLIM-China model, China-Mo is technology-rich side. Technical substitutions are highly reliable compared with IMACLIM-China. For the demand exogenous, China-Mo lacks reflecting the socio-economic structure via the partial equilibrium structure ignores the rebound effects and the intersector impacts. So considering the advantages and the disadvantages of these two models, we also attempt to link these two models to combine their advantages and avoid the disadvantages. Let me first introduce the IMACLIM-China model. It's a global dynamic recursive CG model based on the MPSG language written in GANs. In the IMACLIM-China model, China's economy is divided into 18 sectors, including 6 energy sectors and 12 non-energy sectors. The bottom dataset in the IMACLIM-China model is a hybrid dataset based on China's input-output table 2015, energy balance table in the same year, and we also investigate the market prices of the different energy types. To construct the hybrid dataset, we aggregate the input-output table and energy balance table to the 18 sectors in the IMACLIM-China model. So we can get the original price matrix by dividing the value matrix by the volume matrix. Because the original price matrix is a little different from the market price, we investigate. So we just adjust the original price matrix based on our investigations, and then energy value matrix using the adjusted price times the volume. Finally, we just rebalance the adjusted energy value matrix to get the final hybrid dataset for the model construction. In IMACLIM-China model, the production functions are typical nested CS production function. For non-energy sectors, the classical KLE structure is used to construct the production function. The direct carbon emissions rise are tied to the energy inputs, and the non-CO2 emissions and the industrial process CO2 emissions rise are tied to the product outputs. Meanwhile, the imports and domestic supply are based on the Armington assumptions. Similar as non-energy sectors, the energy sectors in the IMACLIM-China model share similar CS production function and use the KLE structure. The CO2 emissions rise are tied to the energy inputs, and non-CO2 emissions rise are tied to the energy output integers. As we introduced in the background part, the IMACLIM-China model and the China-MO model have complementary advantages. Thus, we also attempt to link these two models. In the IMACLIM-China model transfers the macro results, including GDP sector output, to the China-MO model as input. And the China-MO model transfers the energy system optimization results to the IMACLIM-China model, including energy flows, volumes, price, emission factors, and carbon price is kind of information to the model. Then we just run these two models together until we get a converged status. Finally, I will introduce what the IMACLIM-China model and the China-MO model can do and cannot do. First, these models can simulate China's energy and economic transition pathways for specific emissions targets. Actually, these two models are well designed for the analysis of China's carbon neutral targets. We also can use these two models to assess the economic cost of achieving climate goals and evaluate the impacts of key factors such as energy cost changes and the negative emissions technology developments on the achievements of climate targets. However, the models also have some drawbacks. They are weak in doing global analysis. For these two models, both concentrate on China. Meanwhile, these models cannot do cost-benefit analysis of climate policies right now, for we don't assess the damages in these two models. But we are not put forward these functions, and we hope these two models can do this, do the cost benefits of climate policies as soon as possible. So that's my presentation. Thank you for your listening, and questions are welcome.